Good morning. The Anuruddhan seems to be present as of now. So soon we'll share the screen. Yeah, Soumya has also come. Okay, good morning. Can you see the screen, please?
Morning, sir. Yes.
Yeah, very good. Because I am now taking the class from a new location. I had there's a death in the family, so I am right now in Mumbai. And this week and next week, my taking class could be sporadic. But what I might do is, even if I don't take the class, this continuous time Markov chains, perhaps in 2 installments, I shall send the notes. So my taking class, of course, today I'm able to take, Friday also I hope to. Next week, I am not very sure how many classes I would be able to take. So I might split this thing into 2 installments and send perhaps notes of about 5-6 pages in each installment. Usually I wait for the particular thing to get over before sending the notes. So this time I might do it slightly differently. Let's see how it pans out. So we will be talking about continuous time Markov chains. So we had seen last semester discrete time Markov chains. So, and also till last week, we were seeing a particular type of continuous time process, namely the Poisson process and its manifestations. So today we will look at continuous time Markov chains. Okay. So all continuous time stochastic processes, of course, this is going to be a continuous time stochastic process. If it is going to be a continuous time Markov chain, so that is will be assumed to have right continuous sample paths. What does it mean? Recall that a stochastic process, that is for each, let's say, continuous time process, for each t greater than or equal to 0, a random variable is associated. So if you fix omega, so that is, these are all random variables on some basic space omega. So if you fix a member little omega of capital omega, t going to xt omega with omega fixed is, we will assume that it is the right continuous as a function of t. This kind of assumptions very often one need not make, because by general theory of stochastic processes, which uses quite a lot of measure theory, some of these things can actually be established. That is, there exists a sort of version of the stochastic process for which the sample path is right continuous. So fixing omega, little omega, and considering that as a function of the time variable, that you know that such a thing is called, that function is called a sample path. In the sense that if you draw the graph of that for a fixed omega, it will look like a curve on the x-axis, I mean rather on the t-axis. So we will assume that these are right continuous. So that certain statements which we make and certain, let's say, certain aspects of the proof can be left more or less as exercises. We will also assume that the continuous time stochastic process that we consider is not a trivial process in the sense that it is not an identically a constant. Remember, by technical definitions, such things would also qualify as a stochastic process, but we shall assume that it is not so. Yeah. Please note it down if you want to. Yeah. So now we go to the definition of what is meant by a continuous time Markov chain. So let xt be a continuous time stochastic process, now taking values in integers. So we say this process is a continuous time Markov chain on Z. Z is the state space. On Z, if we have the following. Let us say we fix two time points, S and T. Let's say S is less than or equal to T. And 2 points in the state space Z. So let us say I and J in Z. So X is less than T and I and J are here. And let us say at time yes, the process XS is in state I. And we want to know the probability with which it reaches the state J at time T. So probability that xt equal to J given, let us say S is equal to I. Not only that, we are also given the entire history of the process up to time S. Oh, yeah, for all you inside 0 days. So if you want to say, or rather predict something about the probability of xt taking the value J given the entire past from time S. Not entire thing up to time S. So xu, let us say at any time less than S, it takes the value little x sub u, and xs is at x at time point S, it is at J, that is I. Sorry. So this probability, it is going to be the same as the probability of predicting how the probability that xt would be in J given just the information at that time point S. In other words, this past history does not seem to be relevant. You recall that in the definition of discrete time Markov chain, again, that was the case. There the time was discrete. So if you take it is at the time k and n, let's say n is greater than k, given thing up to k and so on, x0, x1, x2 up to xk, and on basis of that you want to say something about the probability of at x at n, xn is J, then that was the same thing as probability xn equal to J given x k equal to y. So the entire this history is not really needed, provided you know already that it's a Markov chain. This is the Markov property. So this equation we denote by diagram. So please note it. Okay. In addition to the above, if say this probability xt plus s equal to J given xs equal to I, given these things, that is same thing as, let us say here t and s are positive, t plus s we are considering. That is same thing as, that is probability of starting from I at time s and going to t plus s, going to J in at the time t plus s is same thing as probability of starting from I at time 0 and reaching J at time t. That is this difference, t plus S minus S is t. So as you can see, this property is called time homogeneity. So if this happens, the continuous time Markov chain X is said to be time homogeneous. Yeah, please note it down if you want. Yes. So this property, this is the defining property, that is the Markovian property, can also be stated in a different, equivalent. That is, if you have S and T as before and I and J as before, and let us say you fix some integer k, let's say varying, that is 1, 2, 3, etc. Strictly positive integer k, and take k points instead of having the entire history up to time S, you take k points to choose k time points u1, u2, uk between 0 and S. And at these points, let us say one has the value of X. And let's say XL, L running from 1 to K are K points in the state space Z. And suppose you have probability xt equal to J given XUL. At time UL, it is at XL for every L between 1 and K, and at XS, it is equal to I. If that probability is same thing as probability of xt equal to J given XS equal to I. So this property we denote by double dagger. If single dagger holds, then double dagger holds is trivial, because double dagger is a special case of single dagger. Not special case, it's a much more general. Double dagger holds for that, this holds that's for a more general kind of knowledge about the history. But if this holds, then one can show that that also holds. If double dagger holds, single dagger holds, that is because we are assuming all the sample paths are right continuous. So if you choose a dense set of points UK inside 0S, first you fix k equal to 10, then k equal to 20, k equal to 30, and things like that. Then by knowing these things at these points, let's say at dyadic rationals and so on, then you can approximate. And since this is the sample paths are right continuous, the limiting operation will yield the single time. Please note it down if you want to. You have to be careful about writing these things. Yeah. So since the sample paths are right continuous, not difficult to see that these two are equal. Of course, a time homogeneous Poisson process is a time homogeneous continuous time Markov chain on Z. So the Poisson process has the Markov property. Because it has even a stronger property, namely independent increments. Yeah, please note it. So now we will look at an important object. Of course, this is stated in the form of a remark, the holding time. So let xt be a time homogeneous continuous time Markov chain on Z. Suppose at time 0, the process is in state I. Define tau sub I of omega is the infimum t strictly greater than 0, such that xt omega is not equal to the starting point I. For every omega, one defines it. Of course, with the proviso that if for a particular omega there is no such t, that is xt omega always remains in I, then this will be equal to infinity. And by our assumption that the process is not trivial, it becomes clear that for almost every omega, I mean, if you want to be probabilistically correct, almost every omega, but commonsensically sort of say, let's say for every omega, this guy would be, it will not be infinity. It will, for every omega, it will be less than infinity. So probability tau I strictly less than infinity is equal to 1. So that is because we are assuming x is not a trivial process. It's not a constant. Had it been a constant, then there is such possibility. Of course, it can, after some time, it may become a constant or something like that, in the sense that if there is an absorbing state, those kind of things we will see later. That's what happens in the discrete time Markov chain also. If there is an absorbing time, once it reaches the absorbing time, then it never leaves there. I mean, absorbing state, sorry. So tau I is the amount of time the process xt stays in state I before making a transition to a different state. So it is the holding the process, the random time is called the holding time in state I. We have also seen object like this in the discrete time Markov chain. And you may recall that the geometric distribution played a role there. Please note it. So since this is right continuous in t for all omega, this is strictly greater than tau y is strictly greater. Tau y cannot be 0. That is, instantaneously it doesn't leave I. That is because the trajectories are right continuous. All these things, please verify. What happens if, let us say, try to see if suppose tau of omega is 0, then what does it mean? There is a sequence Tn decreasing to 0 such that xTn of omega is different from I. And since the process is right continuous, as Tn goes to 0, that means decreases to 0, that would mean that it at 0 also it should be bigger than I. That is nonsense, because this is supposed to be right continuous and we assume that x0 is I. And also this is also because that the process takes value in Z, which is a discrete space. And the space itself is a continuum, then it can happen that it can leave instantaneously. You will not see that in the case of Brownian motion, but in Brownian motion such things do happen. In the compound Poisson process also this can happen, because it strictly increasing between that two arrival times. Yeah. So now take Tn as positive or non-negative, use the Markov property dagger and time homogeneity and verify. So we will have a chain of equalities now. Yeah. So probability tau sub I strictly greater than t plus s, given that tau is strictly greater than s. So one can write this as x t plus s equal to I, and x at r is also equal to I for all r between s and t plus s, given xs equal to I and xu equal to I with this. So this event basically means that between s and t plus s, the process has not moved from I. And this event means that starting from 0, the process has not moved from I up to time s. It is just that what we have written here in this part, it is precisely this event, and this one is precisely this event. Now using Markov property, you can verify this. Verify that this is the case. And then use time homogeneity to get this. And what we have got here is precisely that probability tau is strictly bigger than t.
Just to confirm, tau is tau I, right?
Oh yeah, sorry, yeah, there is a typo. Yeah, or here also. Yeah, yeah, please, thanks a lot. Please make this correction. This should be tau I, here also tau I. Thanks, Aniruddha. Please note it down with the correction. So this, the final thing, what it means is that probability tau I strictly bigger than t plus s is probability tau I greater than t into this probability tau I greater than s. This also you can verify. It is very simple exercise concerning conditional probability. So this property is called, this is a famous memoryless property. Tau I as the memoryless property. Of course, therefore, it has to be, one knows that, you sort of know that it has to be an exponential distribution. But anyway, we will prove it because I don't know what kind of assumptions were made when you saw the proof that this kind of distributions can only be exponential. So, therefore, we will see how the proof goes. Let G denote the distribution function of the random variable tau. Of course, tau I given x0 equal to I. Consider the random variable tau I given x0 equal to I. So that is a genuine random variable which takes non-negative values, and let G be the distribution function of it. So with this notation, this is what you have here is 1 minus G of t plus s. And similarly here. So this property or this equation asterisk, which is stated in terms of the probabilities of these random variable t greater than t plus s, t, etc. In terms of the distribution function, that can be expressed as 1 minus capital G at t plus s is equal to 1 minus G at t multiplied with 1 minus G at s for all s and t greater than 0. Note that 1 minus capital GT is precisely probability that the random variable tau I takes a value greater than t, strictly greater than t. So this asterisk and double asterisk, they are equivalent. It's the same thing we are expressing in a different language. That's it. Or different notation to be more precise. And we know since G is a distribution function, it is right continuous. So you know from your basic probability course, the distribution function of any random variable is right continuous. Please note it down. Okay, so we claim that 1 minus gt is precisely e to the power minus alpha t for all t positive for some constant alpha which is strictly positive. If alpha is strictly positive, minus alpha is strictly negative. So from this, if we prove this, once we prove the claim, that means that 1 minus gt is the, let's say that the tail of that distribution is e to the power minus alpha t. That precisely is the property of the exponential distribution. This is probability tau I greater than t is e to the power minus alpha t for every t positive. So once we prove this claim, it follows that tau I, the random variable tau I, has an exponential distribution with parameter alpha. That alpha could depend on that I, that state I. After all, our G is the distribution function of tau I. So the dependence of G on I is suppressed here in notationally, for notational simplicity. Okay. So proof. This t going to 1 minus gt is a right continuous function. That's because g is a distribution function. Therefore, g is a right continuous. So again, for notational simplicity, let us write small f at t is 1 minus gt for every t greater than or equal to 0. Note that f1, that is 1 minus g at 1, it is strictly positive. I leave it to you to figure out why. You use one of the assumptions we made right at the beginning, that our process is not a trivial process. The x is not identically constant. So since it is strictly positive, one can write f at 1 as e to the power c for some c in R, for some real number c. Noted. Some of you might have seen the proof of this thing, assuming G is differentiable and things like that, and bringing in some ordinary differential, some properties of ODEs into picture. But this proof is assuming just G is right continuous. And in our context, that may be more relevant. Of course, even once you know some basic analysis, right continuity, one can show. That's what we are going to do. So in that double star, you take T and S both equal to 1. If you do that, then you get F at 2 is e to the power C, the whole thing squared, which is e to the power 2C. I mean, here, when we say we get, please, this means verify that. We get, note that, observe that, it is clearly that it can easily be seen that all these things are verified. Iterate. Take T equal to N, S equal to 1. Then doing some, using this double asterisk, you will get repeatedly F at N plus 1 is e to the power N plus 1 times C. In other words, at every n equal to 0, 1, 2, etc., f of n is e to the power nc. Of course, clearly f at 0 is 1 because it is 1 minus g0. In a entirely similar manner, once again using the double asterisk, verify that for T of the form 1 over n, then it is f at 1, the whole thing raised to the power 1 over n. So which means e to the power 1 over n times c. Please note it down. Yeah, please note. Similarly, one can verify that f at any rational number of the form m divided by n is e to the power m divided by n times for all integers mn. So which means f at any positive or non-negative rational is e to the power rc. And now finally bring in the right continuity property. G and hence of F. So by right continuity of F, it now follows that Ft is e to the power that T times C or C times T for all T greater than or equal to 0. So if since G is a distribution function, note that C has to be strictly negative at C. I leave it to you to verify that this statement. That is a very simple exercise, okay? C has to be strictly negative. C cannot be 0 because then that would make F to be a constant, which is a contradiction, which would contradict various things. And C, if it is C is strictly positive, then this guy will go off to infinity. That cannot happen. Ft as T goes to infinity, this should become 0. So that is because it's a distribution function. G is a distribution function. So 1 minus G has to be 0 as T goes to infinity. So C has to be strictly negative, which means it has to be minus of alpha for some alpha strictly positive. So that completes the proof of the claim. Please note it. So it follows now that Gt is 1 minus e to the power minus alpha t for t greater than or equal to 0 and 0 if t is less than. Oh, sorry, it should be 1, no? If t is less than 0, this should be, oh, G, yeah, this is G. G is a distribution function, so it's 0, it's fine, there is no problem. So tau I has an exponential distribution with parameter alpha. Yeah, there is no problem here, it's correct. So 1 minus G at t less than 0 would be 1. So this parameter alpha in general can depend on I. Yeah, sorry, please note it down. Yeah, so if xi equal to, x0 equal to I, the starting initial state is I, the Markov chain remains there for an exponential holding time tau I, and then jumps to a state j which has to be different from I. So such processes, that is any continuous time Markov chain, is also called Markov pure jump process. For example, in Hoyle, Port and Stone stochastic process, they don't call continuous time Markov chain. The title of that particular chapter is Markov jump process. That is a process which is Markov chain, which takes value in Z. Actually, it can also be proved that if you take a jump process, stochastic process, continuous time stochastic process on Z, I mean continuous time Markov process taking values in Z. So that means that process can can change states only through jumps, because between two these things, it will remain a constant. And then when it changes value, it will be a jump to another state. Such a process will have Markov property if and only if the holding times are exponential. For each I, the holding time is exponential. So this property of exponential holding time characterizes the Markov property. They have intimate connection with Markov property. Of course, the other statement we will not prove. It's beyond the scope of such a course. And we shall stop here for the day. You want me to go back to any of the other previous slides or any questions? I'll be happy to.
So,
Yeah.
just to confirm, we'll have online exam, right?
Pardon?
We'll have an online exam, right?
Final exam?
Yeah.
I don't know. I mean, it is not very clear to me now. So, see, I would like to also finish my portion by hopefully the third week of April. Okay. Anyway, we'll stop sharing. If you don't want me to go back to any of the slides, we'll stop sharing. And whatever you are asking. Yeah. Yes, please. You are saying something. Is it Soumya?
Yes, I just wanted to know that how exam will be conducted.
See, it is difficult to say, because supposing in the midterm exam, if on the basis of that experience, if many faculty people feel that it is better to have an offline exam, then everything could be offline. Okay.
Okay, sir. Yes, sir.
Because see, in general, it might be difficult to judge a person's competence or his grasp of a particular subject in an online exam, because there might always be suspicions, right? So if some people, or let's say a somewhat significant proportion of people, behave in a immature fashion, yielding to temptations, then its ill effect or possible these things may have to be faced by everyone. See, the thing is, yeah, I know what, I hope I don't have to explain any more. You are all quite smart, intelligent people. You can see what I mean, okay? So it is difficult to say at this point. And what I understand from some of the emails, these things is that already some people from on the basis of what they have seen last semester and things like that, they perhaps some of the teachers want to have only offline exam. Okay, so
Yes, sir. Thank you.
if it turns out to be an offline exam, be prepared for even sometimes short notice. Maybe it may be a good idea to come to campus. Whether it is online or offline, you can manage. Okay. So, I mean, in these cases, it is one has to take care of one's own this thing. So, better to play it safe, but maybe to use this opportunity. I think the institute has given the option that, I mean, it says that probably every student, especially your batch, it's a final year batch. So all of you are on the threshold of graduating. So it is the institute might also feel that at least for some time you should be on campus. Whether Mr. So-and-so is actually so-and-so. So I would think to not to leave anything to chance, better to be on campus so that whether it is online or offline, one is prepared. Okay. Beyond that, it is difficult for me to say anything. Okay, so thanks a lot for coming, and this next 2 weeks, this thing is going to be somewhat sporadic, perhaps, but so that there is no real delay in this thing. I shall make sure that the notes at least once a week or something like that you get. Okay, thanks a lot, and we hope to see you on Friday.
Yes,
Are
Okay.
beyond one's control now. Okay. Not only during COVID, even when the COVID seems to be on the wane, there are other kinds of problems now. Had it been completely a regular semester, this online or offline dilemma would not have arisen, right? Every one of you would have been on campus, and I also would have been on campus taking classes sort of face to face. Okay, thanks. Take care. See you all.
Bye, sir. Take care.